I'm not a hardware guy, I'm an algorithms guy. I'm really a neuroscientist doing algorithms. And in practice, as we start thinking about using neuromorphic hardware, whichever of the platforms we're talking about, I think that there are going to be programming hacks that are going to be used. And we've already started thinking through a couple. And I wanted to talk about one, not because I think it's the end-all be-all of how to do neuromorphic computing, but rather because I think it's illustrative of the sort of trade space that we have to worry about across all of our work. So I'll dive in. So when we say neural algorithms, we mean a lot of different things. And in this talk, I'll mean probably one in particular. But there's, of course, deep learning. There's spiking neural algorithms, which is probably what I'm going to talk mostly about. And this is getting algorithms. We've had a few talks of this vein this afternoon. And then there's what I'd call neuroscience-constrained algorithms. So these are really models of the brain itself that are doing things that are useful in the world. This is the Holy Grail. We don't do very much of this as a field. We're hoping to get there. But a lot of what we do and we've been talking about are these two. And in fact, there's a lot going on. I mean, these are, by and large, a lot of Sandia algorithms, but also things that the field has done, liquid state machines, HTM, just general deep learning, and so forth. So the question is, as we look at this landscape of algorithms that exist in the community, this growing plethora of things, where is neural going to have its advantage, right? And so I went back to this. In fact, being fortunate to be on the second day, I think Giacomo had a slide that was very similar to this. And this is kind of obvious, right? I mean, the bigger an application, the more computing resources you use. And it's a very notional sort of concept. But what we're really hoping for in this field is that neuromorphic there will be some intersection point above which, and I would argue most likely it's above a certain point, neuromorphic is going to have some value against conventional. I think that if very simple problems, if I want to sort a few numbers, if I want to add a couple of digits, those small applications are going to be cheaper on CPUs. But there's this sort of, if you overcome this sort of fixed cost in economics terms, then eventually neuromorphic can outscale conventional approaches. And neuromorphic, I really mean a combination of algorithms and hardware. So in a purely notional setting, we're trying to figure out how to get to this side of this size scale. And so I argue that big is what's going to be important. I think we can all come up with a few small examples, but I think by and large we see big examples. I mean, deep learning is the ultimate example of this. Deep learning didn't go very far in the 80s and 90s, arguably because they were stuck with small networks. Come the 2000s and a few tricks by Jeff Hinton and others, they were able to get to very large networks that were able to then become competitive and then surpass more conventional machine learning approaches. We've done at Sandia a matrix multiplication approach. It's a Strawson-based matrix multiplication. Like other Strawson methods conventionally, we see only benefits above a certain scale when things get really large. And then I talked about this last year. I'm not going to talk about any more than this picture here, but we've been looking at random walk Monte Carlo methods for diffusion and solving PDEs. Well, random walk methods for PDEs are fundamentally a large-scale sort of solution. They really only beat conventional approaches above a certain dimensionality. We'll think that neural approaches will excel at this, but that's only going to be once problems get to a certain size. So here's the problem. I think most of the hardware we have today, and in fact a lot of the, like I said, I'm speaking as someone programming it today, I think we're still sitting here on the left. I think that it's not necessarily the fault of the hardware that there's this overhead, but this overhead exists, and we're trying to overcome it. So what are we going to do, right? There are two things to do. One is to reduce the overhead, right? If we bring down this fixed cost, we can do this by obviously having better I/O onto things. On an algorithm side, we can do it by making it more accessible to people. I think Chris in his talk yesterday mentioned that unless you have a Python interface to your platform, no one's going to use it. Well, yeah, that's part of the overhead, right? So making it easier from algorithms. We've been doing this at Sandia with Fugu and Whetstone. The other approach is what I'm going to talk a little more about today, and that is how do we move the hardware over to the right, I guess. And There's obviously hardware stuff, and everyone's taking great care of that, and I'm not going to talk about making hardware better. But I think there are hacks that we can do. There are programming tricks that we can effectively make something that sits over here look like it sits over here. So I'll give an example. So this is a simple neural network. Details don't really matter. But you imagine that this neural network is bigger than your hardware in whatever dimension you care about. Say neuron count, right? You have 1,000 neurons, and there's 5 layers of 1,000 neurons each. What are you going to do? Well, so the issue is that I would argue that by and large, from an outside perspective, memory is cheap. Actually, synapses are fairly cheap. The issue is not can we have more synapses. We can, Moore's law has fed synapse density in a lot of ways. Neurons are, so we can have more synapses. We can easily get to that, 5 layers worth of synapses. Neuron count, of course, there's a fixed cost there, and they're expensive, and we don't really want to scale that up, but we will if we have to. What really matters, and this is what I've learned the more I've looked at this hardware, is that communication is the expense. It's getting all of this information onto these neurons back and forth that really kills you. So it's one of the things you go to NICE a few times, you listen to people, communication is what you learn to pay attention to. And so what we kind of worked out, and we did this a few years ago, is that you could do something like this. You could have the same set of neurons serially now access this information. And this works well if you're not in a streaming application in particular, because the neurons are by and large the same. I mean, they're complicated, but they're relatively homogeneous in many of these deep learning applications. And you basically figure out a way to kind of hot swap out the memory or kind of serially access the memory. And there are ways to do this. And in fact, we've done it on a few different neural architectures. I won't go into that because it's a short talk. But it turns out that you can actually, in a lot of cases, the memory, the synapse number is expensive, or it's cheap. Neurons are really expensive, and you can do stuff like this. So we actually ran into this in Spinnaker. And in Spinnaker, it wasn't the neuron count, it wasn't the synapse count, but it was the sort of communication delivery amounts. And we'll hear more about this tomorrow when Ryan Delina talks. But just notionally, what you end up having is that if you have this sort of set of neurons, and they go through this matrix, and they want to kind of do a vector matrix multiply, and I want to deliver the spikes. And if I have a lot of spikes that have to be delivered at one time step through the routing system, I basically have to throttle back Spinnaker by quite a bit in order to do that, and it still sometimes runs into trouble. But it turns out that you can easily get around this by taking this exact same concept of what we call mosaics, where I can basically split my downstream population and have, it's the same, there are different neurons in this case, but I have different delays. So this population, this has a delay of 1, and this has a delay of 2. And it turns out my spike delivery, my routers only have to deliver spikes at half the rate that they had to before. And of course, I can do this hierarchically. So now I have 4 different rates, right? So some of them are a distance of 1, some are a distance of 2, some are a distance of 3, and some are a distance of 4. So it's a little trick. It's, like I said, it's a hack. And in theory, you're going to build hardware, and Spinnaker 2 probably won't have this problem. But what's going to happen is Spinnaker 2 will have a certain finite size. It'll have a certain limitation of things. And the programmers are going to come up with stuff like this in order to get around it. So it's something to think about in terms of, if you have delays offer you the sort of flexibility in how you can serialize what was kind of effectively a parallel computation. So something maybe to be aware of on the hardware design is that these little tricks, they're good. May as well be able to take advantage of them. Let the programmers hack away. Maybe not engineer towards it, but don't engineer away from it. So kind of thinking more futuristically, here's a crossbar, spike and crossbar, because I like spike and crossbars. And you could do this with crossbars. If we had a talk on 3D integration. So if I 3D stack crossbar memories. Now I can stack them up on top, and if I was feeding a lot of information through all the crossbars at once, I might start melting things. But if I'm doing spikes, they're not going to be that many activated at one time. And if I'm feeding spikes only into one layer at a time, and I kind of cycle through each layer in that same mosaic concept I talked about before, I basically only have effectively one layer being heated up at any given instant. They're spiking, so it's not that much getting heated up. And I can stack these things very densely at that point. I don't have to worry about any of the sort of heat issues going on. So I could potentially take advantage of writing a program of what sequence of these crossbars do I activate, sharing a common population of processing neurons. So this isn't going to work for everything. People's minds are probably like, well, I have this feedback circuit and whatever. And there are ways to probably get that to work in some cases it won't. Dynamics, internal to neurons, you can probably get it to work sometimes and probably not. But I would argue that this is going to work for a lot of applications, especially if we want to broaden beyond sort of the narrow, very brain-inspired applications. And I realize that as a neuroscientist, I probably shouldn't just say that. But so this is a list of things that we at Sandia and others have been coming up with of just very standard numerical operations. These are machine learning operations. These are typical things people would program. It's just a growing list of applications. It does loop through twice, so it's not an infinite list. But it's getting longer. You're not going to see that many repeats. And the ideal is that we would like to, all of these things are using neurons as threshold gates. They're using them as as strong but relatively basic computational units. And if we start assembling them together into applications, so now my algorithms are just a piece of a bigger application, and I want to start packing them together, we're going to push the boundaries of what a single chip could do. And if I'm doing the purple, if I can reuse the neurons that were used for the green, I should be able to do that. And if I can do that, that makes me get more out of that chip than I possibly could. So that's the basic idea there. I'm not going to talk a lot about Fugu. My hope is that we have something like open sourced and the community can contribute to, definitely way before the next NICE workshop. But the idea is basically this is a programming interface to pack all of that long list of algorithms into, and it's coming along pretty well, and interface down into this with the sort of programming interfaces that everyone's been talking about, Pine and Nango and so forth. Fugus, because that's pufferfish. Pufferfish are spiky. I think everyone here can appreciate why the name goes from there. And also, the toxin in pufferfish is tetrodotoxin, which is what electrophysiologists use to silence spikes. Probably fewer people in here know that. So this is just a flow chart for what Fugu looks like. It works. It's starting to exist. This is not entirely vaporware, so we're excited by that. And hopefully soon we'll be able to open that up to the community to start contributing all the sort of exciting algorithms that we've been seeing here and make that list a longer, nicer list, so to speak. And with that, thank you, everybody, and thank you for coming to NICE this year.
OK, thank you, Brad. Questions? Your winners.
Got Mike over here.
Mike.
Yeah, hey, Brad, I'm trying to reconcile this with what we found with Loihi, where we really don't find that the communication is the bottleneck. I mean, it really is the memory of what we can integrate on chip. What you seem to be describing is a very complicated way to get more multiplexing of the communication fabric, but you're not really solving the state problem. You may be reusing some neuron configuration, but you still need extra neuron state. So I think you would just do further multiplexing of the fabric, and you'll just maintain the same non-hacked neural compute model. And I think that would be a much simpler way to do it.
I mean, there are different ways of doing it. That's why I've not stared at Loihi and how we could maybe do this on Loihi. I think that the thing that, and this is kind of the common question that we've had in discussing this kind of somewhat weird idea around Sandia, and that is, if I want to hold neuron state for, I want to use kind of the internal dynamics of neurons and sort of transferring that on and off of neurons is a non-starter, right? So this works really well if I'm not thinking about holding neuron state, and I'm using the neurons really as threshold gates or threshold gates that have maybe that I integrate over for a finite amount of time. I don't know if that gets to your answer. I understand.
So they're not really, OK, so it's just a feed-forward evaluation through the network, and you're just running multiple feed-forward evaluations. There's no state maintained from time step to time step.
So this would not, so there's not a state in the sense of like, say, a liquid state machine. The internal neurons are going to hold their sort of leaky integrate and fire states. That would be one of those cases of an algorithm that does not work on this. But for a lot of the things that we're looking at, where we're looking at not the internal dynamics of neurons are less important than maybe having the architecture and the connectivity to perform the computation. Such as the random walk algorithms we're doing. We don't really need that internal state. And if you don't have to worry about that, you can maybe take advantage of this, depending on the architecture.
Sure. Okay, that's clear. Yeah, for a small set of algorithms, that would work.
It's a growing list of algorithms, and I think that's the thing that surprises me the more we look at it. It's actually a longer list. It's becoming a longer list, faster than the sort of brain-inspired list is growing, unfortunately.
Okay. Okay, thank you very much, Brad. That's